Okay, any questions? This lecture is very important for the exam. Any questions?
No, it's okay.
Go too slow or it's clear? So during the break, somebody did not remember what the base classifier is.
What?
Base classifier.
Huh?
Do you know what it is?
No.
Because it's a very important concept. I think you want to summarize what it is.
Yes.
So, I think this was discussed in the first lecture. If you go back to the first lecture, I'm not 100% sure, but I think it should be there. But in any case, so it's a very important notion because, so it's the best you can do if you have all the information about the problem. So that's the quick summary of what it is, say formally. So the problem involves probability distribution and also a loss function, right? So the loss function is used to measure how much you pay when you mispredict, right? Your output. Supervised learning is all about predicting an input-output relationship. So in the case of binary classification, in the case of classification, the loss is always a 0-1 loss. This is the default. You could change it, but the default is that you pay 1 when you mispredict, and you pay 0 otherwise. And this makes sense in the case of binary classification, right? In the case of multi-class classification. But you could change it. For example, you could decide that every time you mispredict the positive class, you pay $1, and if you mispredict the negative class, you pay 50 cents. The reason being that you care more about getting right the positive class. You can easily imagine a situation in which the loss function changes. But the default is the misclassification of the loss function. So in that case, normally when you speak of base classifier, normally is the function which minimizes the expected misclassification error. Okay? So you take the expectation over x and y from P, the line problem. And well, one way to write it, if let's say that y is 0, 1, so it's binary. Sometimes we use -1, 1, it's binary. Then the classification error, you can just write, that will move for a moment, as y minus f of x squared. Right? So this is epsilon of f. So f is a binary classifier. So f is a function from the input to 0, 1. Right? So f is a function of x, the input space, to 0, 1. And the error of this function, also we call it generalization error, is the expectation of the choice of the input-output from my probability distribution of the loss, right? Now here, y is 0, 1, f of x is 0, 1, so the difference square is always 0 or 1, right? It is 0 when you get it right and 1 when you get it wrong. Is it clear? So, this quantity measures the average error that your classifier encounters on the data, right? And the base classifier is that function which makes this error the smallest possible. Since the probabilistic relationship is probabilistic, the relationship between the input and the output is not deterministic, it's a probabilistic. So, given an input, the output can be 1 or 0 with some probability, right? So there is some randomness. In general, the base error, so the base error is the error of the base classifier, is more than 0, right? And if the relationship is deterministic, it would be 0. And then you do some computations, which at hand I don't remember in detail, but it is simple. Let's try to remember that. And there is a formula for the base classifier, right? So it's which is completely intuitive formula. The formula is that so we call it F base. Right? So, right? The reason that it's based on base rule. What is it? So you say that it's 0 if P of 0 given x is bigger than P of 1 given x. So 1 otherwise. So you do the common sense, right? And right. So then there is a formula which right now I don't remember for the error of the base classifier. Does anybody remember the formula? I think it should be in the first, I be sure on the first line. So basically, right, so if given x, so if P of 0 given x is 0.7, right, and P of 1 given x, it would be 0.3, right, because the sum must be equal to 1. Right? So this will make an error 0.3 30% of the time, right? So then you average these the input space, and that is the error of the base classifier. So there is a simple way to compute it. You cannot do better than that. So the question is, can I mimic the base classifier even on a finite sample using a certain learning algorithm? The one approach is to do density estimation. Right? So that's the base approach. So you come up with a probabilistic model, and you compute P of 0 given x. So x is equal to P of x given 0 and P of 0. So that you need to compute the density. Right? That's one approach, isn't it? I think you have also had this discussed in the first week. These are called generative and discriminative approaches. So if you do some density estimation, this is a generative approach. So you assume some laws about the way that these are generated, and from these laws you derive a model of the density, and then given this density you compute the base classifier for this density. But this base classifier for this density will not be the same as the base classifier of the true density. Right? So you do it, and you have hat of x will be equal to 0 if p hat of 0 given x is more than p hat more than x, and 1 otherwise. But the error of this half hat will not be equal to the base error, it will be something bigger, right? And the question that we ask today, so this is another learning algorithm, right? Based on density estimation. I don't discuss this today, but since during the break there was this question, I think it's important just to clarify. So maybe I digress a little bit too much. Is it clear? So our ultimate aim is to try to mimic the optimal function in the find a function which predicts nearly as well as the optimal predictor. The optimal predictor, the classification, is the base classifier. More generally, the base function, we use a different loss function. So if you have a generic loss function, there will be a base function associated with it. Right? So it's a function which minimizes the expected error, and here you put a different loss function, right? That you still call the base function, but not the base classifier. So classifier is associated with the classification loss. So what we discussed now, so as I said, is statistical learning theory. I don't know why it is called statistical learning theory. But it's statistical because it has to do with statistics. What we talk about today has to do with statistics. But learning theory because it has to do with machine learning. So, this is substantially, this is a statistical problem, but it is a problem which has also interested the machine learning community, starting around maybe the late 80s, early 90s. And in the machine learning community, this is mentioned in one of the next slides, so there was a lot of interest in algorithms, which compute function from data, and computer scientists were unclear about how to assess the learning performance of this algorithm, right? And then there was this field which is called PAC learning, which developed in the late 80s, early 90s. So PAC means probabilistically, approximately correct. Yeah, PAC learning. And so very interesting analyses were developed, which required some probabilistic tools, right? And then in the early 90s, there was this mathematician from Russia, Vapnik, it's called, and also another one, together, Kervonenkis, Vapnik and Kervonenkis, that they have developed a theory of statistical learning theory. They didn't call it statistical learning theory, but then later it was called like that, which was addressing the same problem, right? So, how to control the generalization error of a learning algorithm, a statistical estimator, in a worst case scenario. So, worst case scenario means that the true problem, the P of x comma y, is fixed, right? So, somebody knows it, say God knows it. And this fix is that. So like it's a black box, which is here under the screen, from which you ask me for some data, I take it, I give it to you. Right? So it's fixed. It exists, it's fixed. But we don't know it. You receive the data, and you make your computation, you go to the computer, you implement some vector machine or something else, and you give me kind of an answer, right? So you tell me, I think that this function is a good predictor, right? And then, in order to see if it is a good predictor, I should go to my data, my model, sample new points, and tell you how well it works. Right? But that I don't tell you. I don't tell you. So, what you want to be able to do yourself is to have an upper bound of the performance of this model, this predictor that you find, which is which works no matter what the data generation process is. So there's a worst case analysis, right? So no matter how I generate the data, so the way I generate the data is fixed, but it can be any, right? So it can be adversarial. Actually, I take it back. Adversarial means something slightly different. So maybe what you've seen with markups in online learning. So I take it back. Mistake. So, but the model from which you generate the data, in principle, is fixed, but it can be any. So you like a theory which is still able to tell you that I'm sure that there is a chance of no more than 1% that the performance of the algorithm is worse than something. So this is what is called like a tail bound. So in other words, with at least 99% probability, the performance of my algorithm, the error, will be less or equal than something, right? So you want to be able to make these conclusions, and this conclusion must be true for every data generation process which has been fixed beforehand. It is not exactly like that. So I mean, there are some assumptions which are made here, right? So, but they are mild assumptions. So, for example, you assume that the input cannot be everywhere in the space. You know, they are on a ball, right? You make some little assumption about the data, which are reasonable, right? But essentially, there are no assumptions. Essentially. So you would like to make this conclusion, which are kind of distribution free. So this is the theory which developed in the past, in the early 90s in machine learning. But it draws a lot of ideas from probability and statistics. I would say from probability, right? Because, as I said before the break, classical statistics addresses the issue of generalization on average. So you compute the average of the generalization error rather than try to bound the tail of the distribution. So there will be this parameter delta, which is the confidence parameter. So delta will be small, it will be 1%. Right? So we will see in a moment. Yeah. Okay, so here we start with the fun part. By the way, last week we were about 25 students today. Well, last week was the same number, if you remember, or it was a bit more?
No, about the same.
About the same. Okay. So I think next week we'll be back to the normal class, but check the timetable because there are, I would say, irregular changes. It's not deterministic. Well, it is deterministic after a day. So the reason is that you were many, so there was something went wrong at the beginning, and then it was, you know, when you get something wrong at the beginning, then it's difficult to correct it. So, anyway. So let's say that we have only one function, only one classifier. So f is my classifier, right? So I give you an image, in the classifier times 0, 1, if it is a person or not, right? Or I give you a text document, and the classifier tells me if it is about sport or not. Right? And by the classifier. And epsilon s of f is the error, or is the empirical error on the data set S. Right? So it's the number of misclassified points. Right? So epsilon S of f is the sum I from 1 to n, because n is the sample size. 1 divided by n. Then one way you can write it. Actually, it's exactly as I wrote it before. It's there, right? Using the convention that y and f of x are binary. So this is the classification. This empirical classification error. Okay. Is it clear to everybody? Please interrupt me, because this is very important, and I'm not I'm happy to repeat it. No problem. So here the modus operandi is that we So we ask the following question. What is the chance of me being misled by the function f, by the classifier f? Right? That is, what is the chance that the training error is 0, so we perfectly fit the data with this function, while the true error, or the generalization error, which is the epsilon of f, so it's the expectation, right, of the loss for the choice of the training data from my secret model, which is fixed, but we don't know it. So what is the chance that the empirical error is 0, but the expected error is greater than some epsilon, right? So in other words, what is the probability over the draw of the data S, right? Here the randomness is due by the choice of the training set S. What is the probability that the error, so what is the probability that training error is equal to 0 when the expected error is more than epsilon, right? Now, first of all, the probability of this being equal to 0, right, is equal to the product of 1 minus the error, right? So epsilon of f is the true error of the data, right? So if the error of the function f is 0.1, right? Every time I take a point, I have 90% chances of getting it right, right? And since my points are an identically independent distribution, they are IID, every time I take a point, xy, I apply my classifier to it, I have 90% chances of classifying it correctly, right? So the probability that I classify all the points correctly, which means that the training error is 0, is the product of the probability of classifying correctly each of the points, which is 1 minus epsilon f to the power of n, right? And here I have assumed that this error is more than epsilon, so this is less or equal than 1 minus epsilon to the m, right? And then I use some inequality, which tells me that 1 minus epsilon is less or equal than the e to the minus epsilon, so I get this inequality. This is very simple. It just says that use the convexity of the exponential, so you take the exponential is a negative exponential, right? It does something like that, e to minus x. And then you put the line, which is tangent here. So this is the point 0, 1, right? It's 0, 1. And you have a line here which is tangent, which is 1 minus x, right? So 1 minus x is less than e to the minus x, because it's the lower bound. So that's the way you get 1 minus x is less than e to the minus x. Sorry, 1 minus epsilon. So it will be epsilon. Later epsilon. So you get this bound, right? So the probability of being misled by f, assuming that the error of f, the true error, right, is more than epsilon, is less or equal, so it's a very small number, right? So the bigger m, the smaller this probability, which makes sense, right? So this is very important. It is simple, but it's tricky, so it's important to go slowly. It's slick, it's a slick proof, so to speak. So then you set this equal to delta, right? And you solve from epsilon, right? You take the logarithm, the minus log on both sides, right? So you get, let's do it here, you get the minus log of that is epsilon n equal to the log of 1 minus delta, and then you conclude that epsilon is equal to 1 over n log of 1 over delta, right? And then you turn the bound around, right? So the conclusion of the argument is that the probability at least 1 minus delta, right? The error, the true error, will be less or equal than this quantity. But this is a conclusion of the argument. Okay. as you see, so then we can continue the argument with many functions. Okay? So, right. So what about if we have n functions? Then what we need to do is a union bound. Right? So now we need to look at them one by one, and then the probability of probability that one of them is equal to 0 is less or equal than the sum that each of them is equal to 0. So right, so the question we want to answer is that what is the probability that there exists a function in my, this is also called the hypothesis space. Right? So here the argument will be to within this finite set for the classifier which has the smallest error. Right? What is the probability of being misled by this classifier? Right? So the probability that the error is 0 of one of the functions there when the true error is more than epsilon. Right? And then here you use union bounds, the probability that there exists Fn such that the error of Fn of any data is equal to 0 is less or equal than, so you can see this as an event, right? So this event is a union of events, right? And then the probability of a union of events is less or equal than the sum of probabilities, right? So in each of the individual events is the error of Fn being equal to 0. Okay. So you sum its probabilities. So this is an upper bound to this. And then you repeat the same argument we did in the previous slide, right? So where we were bounding each of this term, right? We were saying that this is less or equal than e to x minus epsilon. Okay? So you just multiply by n, right? So in this case, as you can see, the probability of being misled is larger because it takes a factor of n. Yeah.
The errors, there are different errors for each function. So did you use the biggest epsilon to bound it?
No. Here you use. Let me think about it. So here you use the error of the best function there, right? Because it makes it even bigger. So this quantity will be bigger, right? So if epsilon is small, it will be bigger. So you use the smallest.
Shouldn't you use the error of the most misleading function?
No,
the worst.
The opposite. Because we are looking for the best, you use the best error. Does it make sense?
You're very confident about it. I'm sure it does.
So let's think about it. So, so the key thing here is to use this union bound. But the argument otherwise is exactly as before. So what do you do in this case? Right? So you set, actually it's done here. Let's repeat just like this probability that there is Fn such that epsilon is equal to 0. This is less or equal than n. So, so here again, you set this equal to delta. You want this to be less or equal to delta, let's say. But then you solve for epsilon, right? And you get this. Right? So you get minus log, you get n epsilon equal to log of n over delta, right? And then you get epsilon equal to 1 over n. And this you write as log of n minus log of delta. So what is written? Sorry, log of 1 over delta. But is what is written here. So what you conclude from the argument is that
Excuse me, what's the last thing you wrote?
Log of 1 over delta.
No. I mean the thing you wrote in hand in
This
epsilon equals 1 over m, and what's in
this.
okay.
The same thing. I should not have written it. I just show you how to get here. Right. So what is the conclusion of the argument is that so the probability was less or equal than delta. Then you revert the argument to probability at least 1 minus delta. Right. Probability over the choice of my training set. Right. The generalization error, right, of any function in this case is bounded by this quantity. Now here what you can see is that so if the sample size is large, generalization error becomes smaller. But if this hypothesis space is large, you pay the bound becomes large. Okay. So here you can see that this is the result of doing this union bound. The more functions you have in the space, the harder it is to make the generalization error. So this is the first point where we see the notion of complexity. So the complexity of the space is the logarithm of the number of functions in the space. Okay. Okay. So, any questions? So, I think maybe something I didn't explain well here. So these bounds hold if the underlying model fits the data perfectly. Okay. So here, the way you prove it, you have assumed right, that error is less or equal, greater or equal than epsilon. And you draw a conclusion about the bound, and then revert to this argument to get your confidence bound. So this is pretty much it. So all the rest which follows is a more sophisticated way to address this question when the space of function is not finite but it's infinite or continuous. We don't see that in detail, so this is beyond the scope of the course, but let's just discuss the case in which we have a countable number, countable function class, which in this case is a little bit more tricky, right? Because we cannot repeat the argument we have done here, right? We cannot say that it's less. We cannot do the union bound straight away because this is a series, so n is equal to infinite, so this will not be bounded by a number, right? So then what you need to do is something So we require that, so we consider a countable function class. And then in the argument, we require that the probability of being misled by fn is less or equal than delta times some qn. Right? Before qn was 1 over capital N. But here these qn are numbers which sum to 1. So you kind of weight each function in the space differently, and you assure that the weight sum to 1. That's qn is more or equal to 0. And then you get this bound. So let's repeat the argument slowly. Right? So the probability there exists fm. Right? So this we bound in the same way by the unit bound. This is less or equal. So this is equal to the probability of union. Then sum and probability times s equal to 0. Right, so you require that this is less or equal than qn minus times delta. Right? Okay. And this is equal to the sum over n, and then get qn and then you set equal to delta, and then you get this bound. Now, it's a little bit different, right? Because before here you had the logarithm of n, right? Whereas now we have this logarithm of 1 over qn. So you can see this qn as a measure of the complexity of the function. So the smaller, the larger the complexity. And right, so this is set here. And this is, so you can, the way you can interpret this analysis in the countable case that you have put a prior, right, prior over your space of models, space of functions. And you could imagine that the functions in the space are drawn from some probability distribution, probability with Pn, right? And here, if you put Q equal to P, so if Qn is equal to Pn, that's the optimal way, right, to choose these weights. So this is the starting point of what is called the Pack-Bayes analysis of learning algorithms. So when you have an infinite number of models, you put a prior over the function space, and you draw conclusions, like the one we have drawn before, in the finite case, which involves your prior of the models. The prior is a way to measure the complexity of functions. Okay. So there is much more to say about this, but I can pause. So this is a topic of ongoing activity in the field. So now, this is about classification. And now we discuss in the remaining hour or so discuss how to address these questions in the case of regression. Okay? The regression is more general, so what we say here also applies to classification, of course. And so we just begin with a couple of slides and we make a break. We need to recall some inequalities. And what is called often inequality. So you have random variables, we take value between A and B. Right? So in the case of classification, it would be 0 and 1. So we assume that we do regression, but our output is bounded. Okay. Now, if you have m IAD random variables with psi 1 through psi m, so they are chosen by some probability, which is supported on this interval, between A and B. Then you can ask the question, what is the probability that the empirical average, right, of the sample, right, is deviates from the mean, so mu is the mean of the random variable, by more than epsilon. Right? So you can ask the deviation of the empirical minus the mean, and the mean minus empirical. The conclusion is symmetric. So what often inequality says is that the probability has an exponential, there is an exponential tail bound, which is similar to the one that we saw before, but there are some differences. So this, if b minus a is equal to 1, like in the case of classification, is just 1. Right? So the only difference is that here there is epsilon squared rather than epsilon. Right? Because if you remember before, we were bounding our probability, which is not exactly like this. We see in a moment a wavelength is essentially the same. We're bounding it by e to the minus m times epsilon. Right? But now here, this is a more general result, which holds no matter what the mean is, so that's why you have the epsilon squared. If the mean was equal to 0, you will get epsilon there, which is a better bound, right? Because epsilon is small, so since you square it, it's even smaller, and then this quantity becomes larger, right? And our goal is to make it small. Right? So the epsilon square bound is worse than epsilon. But the reason for which you get the epsilon square is that it's a more general result. So we don't prove this result, but now we describe how to use it for bounding the generalization error over function classes. And again, I discussed mainly the case in which we have a finite function class, and then I mentioned a little bit how to extend this to infinite function classes. So, any questions? So I think we can stop here for 10 minutes.